Good afternoon. I'm Professor Tridibesh Nag from Netaji Subhash Engineering College. I'm about to give a lecture on static VI characteristics of SCR. Now, SCR, as you all know, is a silicon controlled rectifier. It is a four-layered, three-junction PNP semiconductor device consisting of at least three PN junctions, namely J1, J2, and J3. I've named it J1, J2, and J3, functioning as an electrical switch for high power operations. It has three basic terminals called the anode, the cathode, and the gate, which is mounted on the semiconductor layer of the device. Okay, now this is the block which I was talking about. It has got two P layers and two N layers, thus forming three junctions J1, J2, and J3. You can see that the two P layers, these are the two N layers, these are the three junctions. Now the terminal which is nearer to the upper P layer is called the anode. The terminal which is nearer to the lower N layer is called the cathode, and the P terminal which is connected to the P layer nearer to the cathode is called the gate. And this is the symbol for SCR. Now regarding the characteristics of SCR, there are two types of SCR characteristics. The first one is the SCR static characteristics or the VI characteristics, which I will be dealing with extensively, and the other one is the other one is the SCR dynamic characteristics, which deals with the turn on and turn off of the SCR. Okay, now this is the circuit which we require in order to do an experiment for the VI characteristics. The circuit diagram shows that the anode and cathode, this anode and cathode are connected to the supply voltage ES through a load. Another secondary supply EG is applied between the gate and the cathode terminal, which supplies the positive gate current when the switch S is closed. On giving supply, we get the required VI characteristics of the SCR. Now regarding the modes of operation, there are generally three modes of operation. The first one is the reverse blocking mode, then the forward blocking mode, and then the forward conduction mode. Okay, I will deal with all the modes extensively now. Now this is the reverse blocking mode. In reverse blocking mode, the SCR may be treated as open switch. You see, this is the block diagram for the reverse blocking mode. Now here what we will do is that we give a negative supply to the anode, a negative supply to the anode, and a positive supply to the cathode. In this way, and we keep the gate open, that is, we are not giving any supply to the gate. Now at this state, what happens? You see, the junction J1 and J3 are reverse biased, and the junction J2 is forward biased. Okay, now in as a result of this, there will be a very low or very less current of the order of few micro ampere, which will flow from cathode to the anode, and it is called the reverse leakage current. Okay, now it is called the reverse leakage current. Now if we gradually increase the voltage across the cathode and the anode, then what will happen is that there will be a breakdown, avalanche breakdown across this reverse bias junction J1 and J3. Okay, so this part is the characteristics of the reverse blocking mode. Now you see, here it was 0 and we are giving a negative supply to the anode, so it is gradually increasing the current which is flowing through it, very less current, which is called the reverse leakage current. Now gradually, as we are increasing the voltage for a certain critical value of voltage, which is called the reverse breakover voltage, there will be avalanche breakdown across the junction J1 and J3, and there will be huge rush of current, which is shown by this part of the graph, and this is the critical value of the voltage. Okay, now a large current associated with VBR gives rise to more losses in the SCR, which results in heating. This may lead to the thyristor damage, as the junction temperature may exceed its permissible rise. It should be ensured that the maximum working reverse voltage of SCR does not exceed the critical value VBR. When reverse voltage applied across the SCR is less than VBR, the device offers very high impedance in the reverse direction. So in reverse blocking mode, the SCR may be treated as a open switch. Okay, the next is the forward blocking mode. Here also the SCR is treated as a open switch. You see, this is the block diagram. Here we are giving a positive supply to the anode and a negative supply to the cathode, and we're keeping the gate open. Now what happens is that the junction J1 and J3 in this case are forward biased and junction J2 is reverse biased. So again there will be very less current of the order of few microamperes flowing from anode to cathode, which is called the forward leakage current. And this is the characteristics for the forward blocking state. See what happens as we increase the voltage across the anode and cathode, the whole voltage will be applied or will be acting across the SCR, and there will be very less current, which is called the forward leakage current, this part. Now while increasing the voltage, if we reach a certain critical value which is called the forward breakover voltage, the SCR will be turned on or will shift from the forward blocking mode to the forward conduction mode. So this part from 0 voltage till the forward breakover voltage, this part is called the forward blocking mode. Okay, now next we are moving to the forward conduction mode. In the forward conduction mode, it behaves like a closed switch. Okay, now an SCR can be brought from forward blocking mode to forward conduction mode by two methods. The first method is that we can increase the anode to cathode voltage above VBO. This we can increase the anode to cathode voltage above VBO, keeping the gate open, and the other is by applying a gate pulse between the anode and cathode. That is, we have closed the switch and applied a gate pulse. Thus we can turn on the SCR, or we can make it from forward conduction, forward blocking to forward conduction mode at a fixed voltage or a lower voltage below the VBO. Okay, and this is the characteristics. As you can see that from this part to this part is the forward blocking state. As we have reached VBO, as soon as we have reached VBO, the SCR is turned on, and you see the voltage drop across the SCR has considerably reduced. It is of the order of 1 to 2 volt depending on the rating of the SCR. And here this VBO may be 200 or 300 volt depending on rating again. And from this voltage, as soon as the SCR is moving from forward blocking to forward conduction, there is an abrupt fall in the voltage drop across the SCR from 300 volt or whatever it is higher, it is falling to 1 to 2 volt. And another significant change which happens is that here the current across the SCR, that is the anode to cathode current, is very less, and here as soon as it has reached the forward conduction mode, the current begins to increase considerably. Now this is the part how we can if we increase the voltage above the VBO. Now if we keep the voltage say at this point, and we give a gate current IG1, then also at this voltage the SCR will be turned on due to this amount of gate current. If we give this amount of voltage, which is considerably less than VBO, then for this amount of gate current IG2, the SCR will be turned on. By turn on I mean that it will move from forward blocking to forward conduction mode. And again you can see for this amount of voltage the SCR will be turned on if we supply IG3 amount of current to the gate or the pulse to the gate. So if this, as you can see that this IG3 is greater than IG2 and greater than IG1, at VBO your IG is 0, we are not giving any IG, but as soon as we are giving IG, that is the gate current, we can get the thyristor triggered at much lower voltage than the VBO. Okay, now next and this part is the forward conduction mode. This part is the forward conduction mode which I was talking about, and next is the total VI characteristics. Now you see this part, this is the reverse blocking part, and this current, this amount of current is the reverse leakage current. This part 0 to VBO is the forward blocking, this is the forward leakage current, and this is the forward conduction part. And there are two important parameters here. One is the latching current and other is the holding current. Now what is this latching current? Now it is the minimum anode to cathode current required above which the SCR is latched to the on state. By latched, what I mean that it will remain in the on state even if we remove the gate signal. Okay, and the other one, the holding current. This holding current is the minimum amount of anode to cathode current below which the SCR moves in the forward blocking mode. Below this current, the SCR will move into the forward blocking mode. That is, it remains in the off state till the next gate triggering is applied. Now you can ask that what will happen during this part between the latching and the holding current. Okay, in this part, if the current falls below latching current but it is above holding current, if we give a little bit of positive supply, then it will again follow this path. That is, it is not completely in the forward blocking mode. Only below the holding current it will come to the forward blocking mode. Now in the next slide, what I will show you is that the relation between the forward breakover voltage and the gate current. Now you see, as the gate current increases, the forward breakover voltage decreases. At here it is 0, Ig is 0. So we are giving the critical value, that is the VBO, which is specified by the manufacturer. Now Ig1, which is less than Ig3, we are getting less voltage at which the thyristor will turn on, and at Ig3, which is the maximum value, here the voltage is minimum. The voltage required is minimum. Okay, now these are the two parameters which I have already discussed, and thank you. That was it. I hope I have clarified myself. Thank you. Thanks a lot.